A star is heading directly toward our solar system, and it shouldn't be possible to predict something like this with such certainty. But in 2018, the Gaia Space Telescope measured the trajectory of Gliese 710 with such precision that scientists now know exactly when it will arrive, 1,360,000 years from now. When it does, it will pass closer than any star has in millions of years, close enough to unleash a storm of comets that could bombard the inner solar system for millions of years. Let's explore how a star that's moving toward us is quietly rewriting everything we believed about the permanence of our solar system. The Visitor. Somewhere in the dark between the stars, a sun is moving toward us, not drifting, not wandering, but on a confirmed, calculated, measurable path, directly into the neighborhood of our solar system. Its name is Gliese 710, and it is one of the most remarkable objects in the night sky, for a reason almost nobody talks about. It sits there quietly, invisible to the naked eye, a dim orange star about 63 light-years away. Nothing about it looks threatening, nothing about it seems unusual, and yet astronomers who have studied its motion with extraordinary precision have arrived at a conclusion that is difficult to absorb the first time you hear it. This star is coming here. Not metaphorically, not in some loose, astronomical sense of the word. Gliese 710 is physically travelling through the Milky Way on a trajectory that will bring it closer to our Sun than any known star has come in the last few million years. The European Space Agency's Gaia satellite, which spent years mapping the positions and velocities of over 1 billion stars with almost incomprehensible accuracy, confirmed this in 2018 with updated data that actually made the situation more striking than earlier estimates had suggested. Previous calculations placed Gliese 710's closest approach at roughly 1.1 light-years from the Sunday. Gaia revised that figure downward to approximately 0.065 light-years. That is roughly 4,000 astronomical units, placing it well inside what scientists call the Oort cloud, the vast, frozen shell of icy bodies that forms the outermost boundary of our solar system. To put that in terms that carry the appropriate weight, the nearest star to our Sun right now is Proxima Centauri, sitting about 4.24 light-years away. Gliese 710, at its closest, will be more than 60 times nearer than that. It will not strike the Sunday, it will not collide with Earth, but it will pass through our solar system's outermost envelope of material, and the gravitational consequences of that passage are neither small nor fully predictable. What makes Gliese 710 particularly interesting, beyond its trajectory, is what kind of star it actually is. It is classified as a K-type main sequence star, slightly cooler and slightly smaller than our own Sun, burning at a surface temperature of around 4,300 degrees Celsius, compared to the Sun's 5,500. It contains roughly 60 to 65% of the Sun's mass. In the sky of the far future, as it draws closer over hundreds of thousands of years, it will eventually become the brightest star in the night sky by a considerable margin, outshining everything except the Sun itself, glowing with the steady amber light of an approaching ember. There is something quietly unsettling about learning this for the first time. Most people carry a mental image of the solar system as a kind of permanent arrangement. The Sun fixed in space, the planets circling reliably, the stars hanging motionless overhead like lights pinned to a ceiling. Gliese 710 makes it clear that this picture is not accurate. The galaxy is not a still place. It is a system of moving bodies, each travelling on its own course through space, and occasionally, those courses intersect. Most of the time, the distances involved are so vast that even a nearby passage goes unnoticed. But every so often, something comes close enough to matter. Gliese 710. Is that something? It was first identified as a potential close encounter candidate in 1996, when astronomers Joan Garcia Sanchez and collaborators published work identifying it among a group of stars likely to pass near the Sun within the next few million years. It has been studied in increasing detail ever since, and with each new dataset, the picture has only sharpened. The star is real, its approach is real, and the timeline, while long by human standards, is geologically close. The universe, it turns out, is not nearly as static as it appears on a clear night. Stars move, the stars that ancient civilizations used to navigate by, to build calendars around, to weave into mythology. Those same stars are moving. Every single one of them. The night sky, which has been described across human history as eternal, fixed, and unchanging, is in fact a slow-motion river of suns, each travelling at its own speed in its own direction through the body of the Milky Way. The stillness is an illusion, one created entirely by the sheer scale of the distances involved. The stars look motionless because they are so far away. But they are not motionless, not even slightly. The Sun itself is moving. It travels through the galaxy at approximately 828,000 kilometers per hour, orbiting the center of the Milky Way in a journey that takes roughly 225 million years to complete a span of time, sometimes called a cosmic year or a galactic year. The last time the Sun was in its current position in the galaxy, the dinosaurs had not yet appeared on Earth. Before that circuit began again, continents were still being assembled into shapes that modern maps would not recognize. The Sun is not sitting still while the planets orbit it. The entire solar system is hurtling through space at a speed that makes the fastest human technology look stationary. Other stars are doing the same. Each one has what astronomers call a proper motion, a real, physical movement across the sky relative to Earth, as well as a radial velocity, which describes how fast it is moving toward or away from us along our line of sight. Measuring these two values together gives astronomers the full three-dimensional velocity of a star. For most of human history, we had no way of doing this accurately. The angular motion of a nearby star across the sky could be detected with a good telescope over decades, but the radial velocity, the toward or away component, required the development of spectroscopy, the technique of analyzing starlight to detect tiny shifts in the wavelengths of light caused by motion. That technique, refined through the late 19th and 20th centuries, allowed astronomers to begin building a real picture of how stars move. Even then, the precision was limited. Proper motion measurements required years of observations, comparing stellar positions across long-time baselines. Small errors compounded. Distant stars were harder to track than nearby ones. Radial velocities could be measured, but not always with the accuracy needed to predict close approaches millions of years into the future. The predictions existed, but the uncertainty bars were large enough to render many of them tentative. Then came Gaia. Launched in 2013 by the European Space Agency, Gaia is a space telescope with a singular purpose: to map the positions, distances, and motions of stars across the Milky Way with a level of precision that had simply never been achieved before. By 2018, Gaia's second major data release contained measurements for over 1.3 billion stars, including proper motions and parallax distances of extraordinary accuracy. For stars within a few thousand light-years of the Sun, Gaia could determine their positions to within micro-arc seconds, a unit so small that it is equivalent to measuring the width of a human hair from 3,000 kilometers away. This data transformed stellar cartography. Astronomers could now take the positions and velocities of known stars and run them forward and backward in time, tracing their paths through the galaxy with a confidence that earlier generations of scientists simply did not have access to. And when researchers applied this capability to the question of close stellar encounters, stars that would pass unusually near the Sun Gliese 710 emerged at the top of the list, not as a rough candidate with wide error margins, but as a confirmed, well-characterized object on a trajectory that would bring it into the outer reaches of our solar system in approximately 1,360,000 years. The stars were always moving. Gaia simply gave us the tools to finally see where they are going. How close? 4,000 astronomical units sounds like a large number, and in everyday terms, it is almost impossible to picture. 1 astronomical unit is the average distance between the Earth and the Sun, approximately 150 million kilometers. Multiply that by 4,000, and the resulting figure is 600 billion kilometers. By any human measure, this is an enormous distance. And yet, in the language of astrophysics, 4,000 astronomical units is disturbingly close. Close enough that the term near miss is not an overstatement when applied to the predicted passage of Gliese 710. To understand why, it helps to know where 4,000 astronomical units actually sits within the architecture of our solar system. The 8 planets occupy a region extending out to roughly 30 astronomical units, Neptune's average orbital distance from the Sunday. Beyond that lies the Kuiper belt, a disk of icy bodies stretching from about 30 to 50 astronomical units. Further still is the scattered disk, a more distant and sparsely populated region reaching out to several hundred astronomical units. And then, beginning somewhere around 2,000 astronomical units, and extending as far as 100,000 astronomical units or more, lies the Oort cloud, a vast, spherical shell of frozen material, billions of icy objects left over from the formation of the solar system, orbiting the Sun so slowly and so distantly that they take millions of years to complete a single circuit. Gliese 710's closest approach at roughly 4,000 astronomical units places it squarely inside the Oort cloud, not grazing its outer edge, not brushing past its periphery. Inside it, the passing star will move through the outermost reservoir of our solar system's material, and as it does, its gravity, not dramatic, not violent, but persistent and real, will tug at the icy bodies surrounding it. The Gaia revised estimate places the closest approach distance at approximately 0.065 light-years, with uncertainty margins that allow for approaches as close as 0.05 light-years under some models. Earlier estimates from the 1990s, based on less precise data, had placed the figure closer to 1.1 light-years, already considered a close encounter by astronomical standards. When Gaia's measurements arrived and refined this figure downward by a factor of nearly 17, the scientific community took notice. A 2018 paper by Corinne Baylor-Jones and colleagues used the updated Gaia data to confirm Gliese 710 as by far the most significant stellar close encounter expected in the near astronomical future. For context, the next closest confirmed encounter, a star called HIP 89825, is expected to pass at a distance of roughly 0.58 light-years, nearly 9 times farther away than Gliese 710. Most stars that will pass near the Sun over the next few million years will do so at distances measured in full light-years, their gravitational influence on our solar system negligible. Gliese 710 is the exception. It is in a category almost entirely its own. The gravitational effect of a stellar encounter scales with mass, and scales inversely with distance squared. Gliese 710, at about 60% of the Sun's mass, is not a heavyweight, but at 4,000 astronomical units it is close enough that its gravitational pull on the outermost objects in the Oort cloud will be substantial. Simulations suggest that it could directly perturb billions of icy bodies, altering orbits that have been stable for the entirety of the solar system's 4.5 billion year history, sending some inward on long, slow trajectories toward the inner planets. The number 4,000 looks large on paper. Inside the solar system, it represents something altogether different. The timeline: 1,360,000 years from now, Gliese 710 will reach the point of its closest approach to the Sunday. Written as a number, 1,360,000 years feels remote enough to dismiss. It belongs to a scale of time that human intuition is not built to process, a figure so large that it seems to place the event safely in the category of things that do not concern the present. But there is a way of reading this timeline that makes it feel considerably less comfortable, and it begins with a different number entirely. Modern humans, anatomically modern Homo sapiens, the species that builds cities and telescopes and sends machines to the edges of the solar system, have existed for approximately 300,000 years. That is the current scientific consensus, anchored by fossil evidence from sites like Jebel Irhoud in Morocco, where remains dated to around 315,000 years ago represent the oldest known members of our species. 300,000 years is the full span of human existence on Earth, from the first recognizably modern skull to the present moment, including every civilization, every language, every war, every piece of music ever composed. Gliese 710 will arrive in roughly 4.5 times that span of time. Stated differently, if the entire history of Homo sapiens were placed end to end and repeated 4.5 times in succession, the star would be arriving around the conclusion of the final repetition. In geological terms, this is not a distant event. It is practically imminent. The ice ages come and go on timescales of tens of thousands of years. The continents shift measurably over millions of years. 1,360,000 years is the kind of interval over which mountain ranges grow. Species evolve into new forms, and ocean floors are remade. It is not eternity. It is the next chapter. What makes this timeline more striking still is the trajectory of change within the human story. For roughly 290,000 of the 300,000 years of our existence, humans lived as hunter-gatherers, leaving behind stone tools and cave paintings. Agriculture appeared only about 12,000 years ago. Writing is roughly 5,000 years old. The Industrial Revolution began fewer than 300 years ago. The entire arc from first agricultural settlement to the spacecraft currently leaving the solar system fits inside the last 12,000 years, less than 4% of our total existence as a species. The pace of change has not been gradual, it has been exponential, and recently almost vertical. Project that trajectory forward by a factor of 100 and the imagination buckles. 1,360,000 years of continued development. Assuming development continues, produces a civilization whose relationship to the present would be something like our relationship to the microbes that existed before multicellular life. The descendants of humanity, or whatever intelligence inherits this planet or carries human origin into space, will encounter Gliese 710 not as a catastrophe arriving without warning, but as an event that has been known about, studied, and almost certainly prepared for across a span of time longer than our entire current existence. The astronomer Corin Baylor-Jones, whose work with the Gaia dataset established the revised close approach parameters for Gliese 710, has noted that this encounter is unique among known stellar trajectories precisely because of how well constrained the prediction is. Most stellar encounter forecasts carry large uncertainties that grow as the projected time increases. Gliese 710's approach, by contrast, is well determined enough that scientists can speak with reasonable confidence about the encounter geometry even across this vast timescale. The universe keeps its own calendar, and it does not adjust the dates for the convenience of the species doing the watching. The Oort cloud, at the outermost boundary of everything the Sun can reasonably claim as its own, there exists a structure so vast and so thinly populated that it took decades of theoretical work just to convince the scientific community it was real. And the Oort cloud, this enormous spherical shell of frozen debris, sits precisely in the path of Gliese 710's approach. It begins somewhere around 2,000 astronomical units from the Sun and extends outward to perhaps 100,000 astronomical units, roughly 1.5 to 2 light-years in every direction. At that outer edge, the Sun's gravitational hold on its contents is so feeble that a passing star, a molecular cloud, or even the gentle tidal pull of the Milky Way itself can reshape orbits that have remained undisturbed for billions of years. The cloud was first proposed in 1950 by Dutch astronomer Jan Oort, who noticed something peculiar about long-period comets, those icy visitors that sweep through the inner solar system on orbits, taking thousands or even millions of years to complete. Their arrival directions were essentially random, coming from all points on the celestial sphere rather than from the flat plane of the solar system where the planets orbit. Oort reasoned that this could only mean their source was a spherical reservoir, not a disk, and that this reservoir must lie at an enormous distance from the Sunday. The cloud that bears his name has never been directly observed. No telescope has resolved individual objects within it. Its existence is inferred entirely from the behaviour of the comets it periodically releases inward, which is itself a rather extraordinary way for something to be confirmed. The population of the Oort cloud is estimated at somewhere between 100 billion and several trillion individual objects, comets, icy planetesimals, and frozen remnants from the earliest period of the solar system's formation. They were not born where they now reside. Most are believed to have formed in the region between Jupiter and Neptune, where the raw material for planets was abundant and the conditions for icy body formation were suitable. Over millions of years, gravitational interactions with the giant planets scattered these objects outward, and the gentle influence of passing stars and galactic tides gradually rounded their orbits into the vast sphere we infer today. Each of these objects is essentially in a state of suspended hibernation. They travel in orbits so large that their closest approach to the Sun, if undisturbed, would never bring them anywhere near Earth. They are cold, dark, and silent, sitting at temperatures just a few degrees above absolute zero, carrying within them some of the most pristine material in the solar system: water ice, carbon dioxide, methane, and complex organic compounds essentially unchanged since the solar system was 4.5 billion years young. Gliese 710 will pass through this shell. At roughly 4,000 astronomical units well within the inner Oort cloud, the star will spend hundreds of thousands of years traversing our solar system's outermost envelope, its gravity continuously tugging at objects whose orbital stability depends on being disturbed by nothing more significant than the slow background pull of the galaxy. A star passing through is not a background force. It is a gravitational intruder, and the objects it perturbs do not simply wobble and return to their original paths. They are redirected, placed on new trajectories, some of which will send them falling inward across the vast distance between the Oort cloud and the Sun over thousands and tens of thousands of years. The Oort cloud has kept its frozen inventory largely intact for nearly the entire history of the solar system. What Gliese 710 represents, in the most precise terms available, is the largest external gravitational disturbance that inventory has encountered in recorded astronomical history. The comet storm. Long before the first comet arrives, the process will have already begun in silence. The comet storm that gravitational models associate with a close stellar encounter like Gliese 710 does not start with anything visible. It starts with a shift in orbital mathematics, deep in the frozen dark, where objects that have been travelling on stable ellipses for billions of years find those ellipses subtly, irreversibly altered. Simulations of close stellar encounters with the Oort cloud, including work published by researchers such as Julio Fernandez and Hans Rickman, suggest that a passing star at the distance Gliese 710 will achieve could redirect tens of billions of cometary objects. Not all of them will head inward. The geometry of gravitational perturbation is not a simple funnel pointing toward the Sunday. Most displaced objects will simply be flung outward, some entirely out of the solar system, added to the population of interstellar objects drifting between the stars. But a significant fraction estimates vary, with some models suggesting an increase in cometary flux by a factor of 10 or more above current background levels will be sent on orbits that bring them through the inner solar system. The timescale of this delivery is important. The objects perturbed during Gliese 710's closest approach will not arrive simultaneously. A comet nudged from the inner Oort cloud at a few thousand astronomical units on an orbit directed inward might take anywhere from 1 million to 10 million years to complete its first pass through the inner solar system. The actual period of elevated comet flux is expected to last millions of years after the encounter, a slow, extended pulse of incoming material rather than a single concentrated event. For context on what elevated cometary bombardment means in practice, the late heavy bombardment, a period roughly 3.9 billion years ago, when the inner solar system experienced an intense spike in impacting bodies, possibly triggered by a gravitational reshuffling of the giant planets, left scars across the Moon, Mercury, and Mars that are still clearly visible today. The lunar surface, as it appears now, covered in overlapping craters, is largely a product of that era. The late heavy bombardment is thought to have delivered significant quantities of water and organic material to the inner planets, and it may have played a role in the conditions that eventually gave rise to life on Earth. It also, depending on its intensity, likely sterilized or severely disrupted any early biological processes that had begun. A comet storm does not require objects of enormous size to have consequences. A comet a few kilometers across, striking Earth at typical encounter velocities of several tens of kilometers per second, releases energy equivalent to billions of nuclear weapons. The Chicxulub impactor, which ended the Cretaceous period 66 million years ago and took the non-avian dinosaurs with it, was estimated at roughly 10 to 15 kilometers in diameter. It is not the largest object in the Oort cloud by a considerable margin. What the models do not yet resolve with precision is the exact number of objects that Gliese 710's passage will redirect, because the total population of the Oort cloud remains uncertain to within orders of magnitude. The range of projected outcomes is correspondingly wide, but the direction of the effect is not in dispute. The encounter will increase the rate at which Oort cloud objects are delivered to the inner solar system. The only genuine uncertainty is the magnitude of that increase, and the duration over which future inhabitants of this planet, whatever form they take, will need to account for it. It's happened before. The solar system's surface history is not smooth. Look at the Moon through any reasonable telescope, and what you see is not an ancient unmarked sphere. It is an archive of violence, a record of impacts stretching back almost to the beginning, written in craters that range from microscopic pits to basins hundreds of kilometers across. That record exists partly because the Moon has no atmosphere, no weather, no plate tectonics to erase what was done to it. What was written there has stayed written. And what was written tells us, clearly and without ambiguity, that the inner solar system has been bombarded many times over its history, in patterns that researchers have been trying to explain for decades. Some of those patterns point outward toward the Oort cloud, and toward the stars that have passed near enough to disturb it. The most studied episode of elevated bombardment is the late heavy bombardment, which appears to have peaked around 3.9 billion years ago. The lunar surface shows a concentration of impact basin ages clustering in this window, a feature noticed and named by teams analysing rock samples returned by the Apollo missions in the 1970s. Why the bombardment intensified at that particular moment, hundreds of millions of years after the solar system formed, has never been fully settled. The most widely accepted explanation involves the migration of the giant planets, particularly Jupiter and Saturn, settling into their current orbital resonances, which destabilized the asteroid belt and sent a wave of material inward. But stellar encounters have been proposed as a contributing factor, with passing stars perturbing Oort cloud objects on timescales that could align with the observed spike. More directly relevant are statistical studies of stellar encounter rates. Work by researchers including David Nisvorny and others modelling the Sun's galactic trajectory suggests that close stellar encounters within 1 to 2 light-years have occurred roughly 10 times over the solar system's lifetime, with several likely approaching within the inner Oort cloud's range. These encounters leave no permanent address, no crater, no obvious physical scar on the planets. Their traces are instead embedded in the statistical distribution of cometary orbits, in the asymmetries of the Oort cloud's population, and in elevated impact rates that pulse through geological and fossil records at intervals that have attracted considerable attention. There is a body of research, associated particularly with the work of Michael Rampino and Richard Stothers in the 1980s, that identified a possible periodicity in mass extinction events of roughly 26 to 30 million years. The data underpinning this claimed periodicity has been debated at length, and the statistical significance of the pattern remains contested. But the attempt to explain it produced one of the more remarkable hypotheses in modern astrophysics, a hypothesis that connects the Sun, the Oort cloud, and the history of life on Earth through a single proposed mechanism. There is also the direct physical evidence embedded in the solar system's smaller bodies, the orbits of known long-period comets carry encoded in them the gravitational history of their source region. Statistical analyses of these orbits, particularly the clustering of orbital energies near zero that Oort originally noticed, suggest a source population that has been repeatedly disturbed by external forces consistent in character and frequency with the known rate of stellar encounters. The solar system has, in other words, been here before. Not in the specific sense of a star named Gliese 710, but in the general sense of an outer reservoir nudged by passing gravity, comets redirected, the inner system exposed. That history did not end life. In some periods, it may have created conditions that supported it. The same impacting bodies that crater surfaces also deliver water, carbon compounds, and complex molecules, the raw ingredients that origin of life chemistry requires. The Nemesis star. In 1984, 2 papers appeared almost simultaneously in the journal Nature, each proposing the same disturbing idea through slightly different reasoning. One was authored by Mark Davis, Piet Hutt, and Richard Muller, the other by Daniel Whitmire and Albert Jackson. Together, they introduced what became known as the Nemesis hypothesis, the proposal that the Sun is not alone, that it has a companion star, dim and distant, and as yet undetected, whose periodic passages through the Oort cloud trigger comet showers that rain down on the inner solar system at regular intervals, causing the mass extinctions that have punctuated the history of life on Earth. The hypothesis was built on a foundation laid by paleontologists David Raup and Jack Sepkoski, who had published a landmark analysis in 1984, examining the timing of marine animal extinctions over the past 250 million years. Their analysis identified what appeared to be a recurring pattern in extinction intensity, with peaks spaced approximately 26 million years apart. Raup and Sepkoski were careful about their interpretation, but the implication was arresting. If extinctions were periodic, something periodic was causing them. Orbital mechanics are the most reliable source of periodicity in the universe. Nemesis, as the papers proposed it, would be a red or brown dwarf star, cool, faint, and therefore easily missed by sky surveys of the era orbiting the Sun at a distance of somewhere between 90,000 and 150,000 astronomical units, in a highly elliptical orbit. Every 26 million years, its orbit would carry it through the inner Oort cloud, gravitationally disturbing the resident population and triggering a comet shower that would persist for millions of years, during which the probability of a major impact on Earth would rise substantially. The hypothesis was scientifically serious enough to generate dedicated search programs. The infrared astronomical satellite, known as IRAS, launched in 1983 and conducted an all-sky survey that would have been capable of detecting a bright red or brown dwarf at the proposed distance. Nothing was found. Subsequent surveys, including the more sensitive 2-micron all-sky survey and eventually the wide-field infrared survey Explorer WISE, extended the search with significantly greater sensitivity. WISE, which completed its primary survey in 2011, was capable of detecting brown dwarf stars far dimmer than Nemesis was hypothesized to be. It found none in the Sun's vicinity at the proposed distance. The periodicity in the extinction record has also been challenged on statistical grounds. Studies applying more rigorous methodology to the Raup-Sepkoski dataset have found the 26 million year signal either absent or considerably weaker than originally claimed, and the dating uncertainties in the fossil record are large enough to accommodate a wide range of proposed periods. The hypothesis, while never formally disproven, has faded from the active research agenda. What connects Nemesis to Gliese 710 is not the specific hypothesis but the mechanism it describes. Whether or not the Sun has an undiscovered companion, the process Nemesis was proposed to achieve a star passing through the inner Oort cloud, dislodging comets, elevating impact rates on the inner planets is precisely what Gliese 710 is confirmed to accomplish. Nemesis was theoretical. Gliese 710 is observational fact. The star that astronomers spent years searching the sky for turns out to be approaching from outside the solar system entirely, visible, measurable, and tracked to within the precision of micro-arc seconds. The universe occasionally makes the hypothetical concrete, and it does not always ask permission first. Dinosaur connection. 66 million years ago, something ended. The reign of the non-avian dinosaurs, and the connection between that catastrophe and the movement of stars through the galaxy is not as remote as it might first appear. The Chicxulub impactor, the object whose collision with what is now the Yucatan Peninsula of Mexico released energy equivalent to roughly 10 billion nuclear weapons and triggered a global winter that collapsed food chains across the planet, was either an asteroid or a comet. The distinction matters more than it might seem, because asteroids and comets come from different places, travel on different kinds of orbits, and arrive in the inner solar system through different mechanisms. If Chicxulub was a comet, or if it was an asteroid whose orbit was destabilized by a comet shower, then the question of what sent it inward becomes considerably more interesting. The case for a cometary origin of the Chicxulub impactor was argued in detail by Harvard astronomers Amir Siraj and Avi Loeb in a paper published in 2021 in the journal Scientific Reports. Their analysis focused on a class of objects known as long-period comets, those originating in the outer solar system on orbital timescales of thousands to millions of years, and examined what happens to them when they pass close to Jupiter. The giant planet's gravity can tidally disrupt these objects, fragmenting them into smaller pieces and simultaneously altering their orbits in ways that increase the probability of an Earth-crossing trajectory. Siraj and Loeb calculated that this mechanism could account for a significant fraction of large impact events in Earth's history, including, potentially, Chicxulub itself. What sends long-period comets into the inner solar system in the first place is, at its root, a question about what disturbs the Oort cloud. Galactic tides, the slow, rhythmic gravitational influence of the Milky Way's mass distribution on the solar system, do some of this work continuously. Giant molecular clouds, when the solar system passes through or near them during its galactic orbit, can perturb Oort cloud objects in large numbers. And stellar encounters, which deliver a gravitational pulse to the outer reservoir every time a star passes within a few light years, can redirect billions of objects at once. The solar system has completed roughly 20 complete orbits of the Milky Way since its formation, each taking approximately 225 million years. Over that time, the Sun has passed through regions of varying stellar density, encountered molecular clouds of varying mass, and experienced close stellar approaches at a rate estimated at roughly 1 per 100 million years for passages within 1 light-year. That is a rate entirely consistent with producing periodic disturbances in the Oort cloud at intervals that overlap with the patterns observed in the fossil extinction record. Whether any specific stellar encounter can be directly connected to Chicxulub is, at present, beyond the resolution of available data. Tracing the precise galactic trajectory of the Sun 66 million years back in time, and identifying which star occupied which position in space at that moment, requires a level of positional and velocity precision for the full stellar neighbourhood that current instruments, including Gaia, cannot yet provide for distances beyond a few thousand light-years. The chain of causation stellar encounter, Oort cloud disturbance, comet shower, specific impactor, mass extinction, is physically plausible at each link. Whether all the links connect for the Chicxulub event remains an open question. What the Siraj and Loeb analysis does establish is that the mechanism is real, that long-period comets arrive in the inner solar system in greater numbers during periods of elevated Oort cloud disturbance, and that the largest craters on Earth cluster in ways that suggest periodic external forcing. The dinosaurs may have been ended not by a random cosmic accident, but by a process that had been building across millions of years, driven by forces operating far beyond the edge of the solar system. Rogue planets. Between the stars, in the darkness that stretches for light years in every direction, there are planets travelling alone. They have no sun. They orbit nothing. They were either ejected from their birth systems by gravitational interactions with larger planets, or they formed in isolation from dense patches of gas and dust that were too small to ignite into stars. These are rogue planets, free-floating worlds wandering through the galaxy in silence, and the possibility that Gliese 710 may be travelling in the company of one or more of these invisible objects introduces a dimension to its approach that optical observations alone cannot fully address. The existence of rogue planets is not hypothetical. Gravitational microlensing surveys techniques that detect the bending of background starlight by a foreground mass, regardless of whether that mass emits any light of its own, have identified candidates for free-floating planetary mass objects throughout the galaxy. A 2011 study published in Nature by Takahiro Sumi and colleagues, using data from the microlensing observations in Astrophysics Survey, estimated that Jupiter mass rogue planets might be nearly twice as common in the galaxy as main sequence stars. A 2021 analysis using data from the optical gravitational lensing experiment identified additional candidates, including objects potentially as small as Earth or Mars in mass. The formation of rogue planets in any given stellar system is a natural consequence of planetary formation dynamics. When multiple large planets form and gravitationally interact, the least stable member of the system is often ejected on a hyperbolic or barely unbound orbit. Computer simulations of solar system formation regularly produce ejected objects, and the same is expected to be true for Gliese 710's system, which, like most K-type stars, is assumed to have formed in a stellar nursery with nearby neighbours, gravitational interactions, and the full complement of formation-era chaos. Whether Gliese 710 currently hosts rogue companions objects that were ejected from its own planetary system long ago but remain loosely gravitationally associated is not known. At 63 light-years, detecting substellar objects around Gliese 710 at the distances where such companions might travel is at the very edge of current observational capability. A rogue planet loosely bound to Gliese 710 would not necessarily travel in a tight orbit around it. It might wander several light-years from the star on a weakly bound trajectory, making its detection and its association with Gliese 710 extremely difficult to confirm. The concern is not trivial. A rogue planet entering the solar system on a trajectory that differs from Gliese 710's by even a small angle could approach regions of the solar system that the star itself will never reach. At planetary masses, a rogue body would not exert the same large-scale gravitational influence as a stellar encounter, but a direct orbital interaction with Neptune, Uranus, or even the asteroid belt would carry consequences far more immediate than the slow perturbation of distant Oort cloud objects. The trajectories of known solar system bodies could be measurably altered by a close passage. An impact on one of the outer planets, or on a large Kuiper belt object in a way that deflected it inward, would be an event on a different order entirely. For now, the absence of evidence is not evidence of absence. The instruments capable of detecting a cold, dark, planetary mass object at interstellar distances do not yet fully exist. The Nancy Grace Roman Space Telescope, expected to launch in the mid-2020s, will conduct gravitational microlensing surveys of unprecedented sensitivity and is expected to find thousands of rogue planet candidates across the galaxy. Whether any of them travel with Gliese 710 is a question the next generation of surveys may be positioned to answer. The galaxy is not empty between the stars. It is filled with things that carry no light of their own. Gravity tug-of-war. A star does not need to touch anything to change everything. Gravity reaches across empty space with perfect indifference to distance weakening with the square of separation, yes, but never truly stopping, never switching off, acting continuously on every object in its vicinity, whether that object is a boulder in the Kuiper Belt or a planet the size of Neptune. When Gliese 710 passes through the outer solar system, it will not need to come anywhere near the inner planets to participate in what is effectively a tug-of-war over the solar system's architecture, pulling gravitationally at objects whose orbits have been shaped and maintained by the Sun's dominance for 4.5 billion years. The outer planets are the most exposed. Neptune and Uranus, orbiting at roughly 30 and 19 astronomical units respectively, sit at the inner boundary of the region most directly affected by a stellar encounter. Numerical simulations of close stellar flybys, including work by Nathan Kaib and Thomas Quinn, published in 2008 in the journal Icarus, examined how encounters at distances comparable to Gliese 710's projected closest approach affect the orbital parameters of the outer solar system. Their models found that encounters within several thousand astronomical units can produce measurable, permanent changes in the orbital eccentricities and inclinations of the outer planets. Not catastrophic changes. Not changes that would be visible to a casual observer over a human lifetime. But changes that, over millions of years, would propagate inward through gravitational coupling and potentially destabilize portions of the asteroid belt and Kuiper Belt. The mechanism works through a process called secular perturbation, where the gravitational influence of a passing body slowly shifts the shape and orientation of an orbit, rather than delivering a sudden kick. An orbit that has been essentially circular for billions of years becomes slightly elliptical. An orbit that lies flat in the plane of the solar system tilts by a small angle. These changes accumulate and interact with one another. Jupiter's enormous gravitational influence on the inner solar system means that any significant shift in its orbital parameters propagates throughout the inner planets. And while Jupiter itself is unlikely to have its orbit fundamentally altered by a stellar encounter at 4,000 astronomical units, the mathematical sensitivity of interconnected orbital systems to small external perturbations is well established. There is also the question of the asteroid belt. The belt between Mars and Jupiter is not a uniform cloud of evenly distributed material. It is structured by resonances with Jupiter orbital periods that stand in simple mathematical ratios to Jupiter's own orbit, creating regions of instability from which asteroids are regularly ejected inward. A small shift in Jupiter's orbital eccentricity, even by a fraction of a percent, changes the positions and strengths of these resonances, effectively redrawing the map of which asteroid orbits are stable and which will eventually deliver their occupants to the inner solar system. Gliese 710 will also interact gravitationally with the Kuiper Belt, the disk of icy bodies beyond Neptune. At its closest approach of approximately 4,000 astronomical units well beyond the Kuiper Belt's outer edge, at around 50 astronomical units, the star's direct influence on individual Kuiper Belt objects will be modest but non-zero. Combined with any orbital shifts in Neptune, which acts as the gravitational shepherd of the Kuiper Belt's outer boundary, the downstream effects on the distribution of Kuiper Belt objects could persist for hundreds of millions of years. None of these effects will be detected during the encounter itself. The solar system will look from the inside much as it does today. The changes will unfold across timescales measured in millions of years, playing out in orbital shifts too slow for any individual generation to observe directly, writing themselves into the long-term statistical behavior of the solar system's smaller bodies. Gravity does not announce itself, it simply adjusts the terms. Will Earth survive? The direct answer, based on the best available modelling, is yes, Earth will survive the passage of Gliese 710. The star will not come close enough to significantly alter Earth's orbit, will not strip away the atmosphere, will not gravitationally dislodge the Moon, and will not do any of the things that the word approach might suggest when applied to a stellar object. Earth will still be here. The Sun will still be here. The inner solar system will remain recognizably intact. That much the simulations say clearly, and it is worth saying clearly, because the qualifications that follow are not small. The most comprehensive modelling of Gliese 710's effects on the solar system comes from work by researchers including Corinne Baylor-Jones, Philip Bursky, and Łukasz Wysoczyński-Rubel, the latter two publishing in 2017 and 2023 respectively, drawing on successive Gaia data releases. Their analyses examine not only the most likely closest approach distance, but also the full range of possible encounter geometries within the uncertainty bounds of current measurements, producing probability distributions for different outcomes rather than single predicted values. Within those distributions, the most probable scenario leaves the orbits of the 8 major planets essentially unchanged. The encounter at 4,000 astronomical units is simply too distant to deliver a gravitational impulse to the inner solar system strong enough to overcome the Sun's dominant influence on objects at Earth's distance. Approximately 1 astronomical unit, the ratio of the Sun's gravitational pull on Earth compared to Gliese 710's pull at closest approach, is many orders of magnitude in the Sun's favour. Earth's orbit will not measurably shift. The risk is indirect, and it operates on a timescale that stretches millions of years beyond the moment of closest approach. The comet shower, triggered by Gliese 710's passage through the inner Oort cloud objects redirected from stable, million-year orbits onto new trajectories aimed at the inner solar system, will deliver elevated numbers of long-period comets into Earth-crossing orbits for an estimated period of between 2 million and 4 million years following the encounter. During this period, the probability of a large cometary impact on Earth will be higher than at any point in recent geological history. How much higher is the figure that carries the widest range across different models? Simulations by John Matisse and Daniel Whitmire, and later updated analyses incorporating Gaia data, suggest that the flux of Oort cloud objects entering the inner solar system during the peak of a disturbance event could be 10 to 40 times the current background rate. Not all of these objects will cross Earth's orbit. Not all Earth-crossing objects will impact. But the cumulative probability of at least one major impact event, an object of Chicxulub scale or larger during a multi-million-year window of elevated flux, is not negligible by any honest calculation. The uncertainty in this figure is large. It depends on how many objects Gliese 710 actually perturbs, which depends on the total population of the Oort cloud, which remains uncertain to within factors of several. The range of outcomes in existing models spans from modest inconvenience to an extinction-level bombardment period, and current data cannot fully distinguish between these possibilities. Earth will survive Gliese 710. Whether everything living on it at the time will be quite so fortunate depends on a number of variables that will take the better part of 1 million years to fully resolve themselves, and somewhat longer still to arrive. The speed secret. Part of what makes Gliese 710 so difficult to intuitively grasp as a threat is embedded in its speed, or rather, the deceptive lack of it relative to us. The star is approaching the solar system at approximately 14 kilometers per second. That sounds considerable until you compare it to the typical velocities of stars moving through the galaxy, which average somewhere between 20 and 40 kilometers per second relative to their neighbours. Gliese 710 is, by stellar standards, moving slowly, almost gently, and this slowness is precisely what allowed it to go undetected as a serious encounter candidate for so long, and what makes its gravitational impact on the solar system, when it finally arrives, more significant than a faster-moving star at the same distance would be. The relationship between encounter velocity and gravitational effect is not immediately obvious but is deeply consequential. When two objects pass each other, the slower the relative velocity, the longer each spends within the other's gravitational sphere of influence. A star passing at 40 kilometers per second spends roughly half the time within a given distance compared to one moving at 20 kilometers per second. Less time means less accumulated gravitational impulse delivered to nearby objects. Gliese 710's low approach velocity means it will spend an extended period in the vicinity of the solar system's outer reaches long enough to deliver a gravitational perturbation to Oort cloud objects that faster-moving stellar encounters simply cannot match at equivalent distances. This is described in orbital mechanics through a quantity called the gravitational impulse, sometimes written as a function of the star's mass divided by its velocity and its closest approach distance. For Gliese 710, all three variables combine unfavourably. The mass is substantial at 60% of the Sun's. The closest approach distance is small, by stellar encounter standards, and the velocity is low. The product is a gravitational disturbance that researchers, including those working with the Gaia data, have consistently placed among the largest expected for any stellar encounter in the next several million years. The detection problem compounds this. Early identification of approaching stars depends on measuring two quantities: their angular motion across the sky, called proper motion, and their velocity along the line of sight toward or away from Earth, called radial velocity. A star moving directly toward us shows almost no proper motion at all. It appears nearly stationary against the background sky, barely drifting from year to year, because it is approaching rather than crossing. Its radial velocity tells the story, but radial velocity measurements require spectroscopic observations of sufficient precision, and early stellar catalogues lack the sensitivity to flag Gliese 710 as unusual. The star was first properly identified as a close encounter candidate only in 1996 by Garcia Sanchez and colleagues, using data from the Hipparcos satellite Gaia's predecessor, launched in 1989. Even then, the estimated closest approach distance carried uncertainties wide enough to place it at over 1 light-year in some models, which is notable but not alarming. It was not until the second Gaia data release in 2018, with its vastly improved proper motion and parallax precision, that the closest approach figure was revised down to 4,000 astronomical units, and the full character of the encounter became clear. A star moving slowly enough to look nearly stationary, approaching from a direction that suppresses its apparent motion, at a distance requiring sub-milli-arc-second astrometry to properly characterize Gliese, 710 hid in plain sight, not through any cosmic intention, but through the straightforward geometry of its trajectory. The sky contains thousands of stars closer than 100 light-years. Without instruments precise enough to measure motion at the level of individual micro-arc-seconds per year, most of their future paths remain unknown. Gliese 710 was found because the technology finally caught up to the problem. Other incoming stars. Gliese 710 occupies the top of a list that most people have never heard. Exists a catalogue of stars confirmed to be on trajectories that will bring them into the near vicinity of the solar system within the next few million years. A list built almost entirely from the extraordinary positional and velocity data delivered by the Gaia mission. The star's approach at 4,000 astronomical units places it in a category largely its own, but the catalogue surrounding it contains dozens of other objects, each with its own encounter geometry, each a reminder that the solar system moves through a galaxy that is not uniformly empty. The second most significant confirmed encounter in the near future involves a star designated HIP 89825, which is expected to pass at approximately 1.5 light-years from the Sun in roughly 4.3 million years. At that distance, its gravitational influence on the Oort cloud will be measurable but considerably more modest than Gliese 710's, operating primarily at the cloud's outermost fringes rather than penetrating its interior. A 2018 paper by Baylor Jones and collaborators, using the full Gaia data release 2, identified over 700 stars that will pass within 16 light-years of the Sun over the next 5 million years, with a subset of around 50 coming within 3 light-years. Further back in time, the record of past encounters is equally populated. The same Gaia-based analyses that project future stellar trajectories also allow researchers to reverse the clock and identify which stars have already passed close to the Sunday. A star designated HIP 85605, a red dwarf, appears to have passed approximately 0.37 light-years from the Sun, approximately 2.8 million years ago, considerably closer than Gliese 710's projected approach, and well within the inner Oort cloud. If its encounter parameters are accurate, it represents the closest confirmed stellar passage in the solar system's recent geological history, arriving during the Pliocene epoch on Earth, roughly contemporaneous with the early ancestors of genus Homo. Looking further into the future, beyond Gliese 710's encounter, models of the Sun's galactic orbit suggest that the rate of close stellar encounters will not remain constant. As the solar system completes future orbits of the Milky Way and passes through regions of varying stellar density, including the spiral arms, where star formation is active and stellar populations are denser, the frequency of close encounters is expected to rise during those passages and diminish during intervals spent in the interarm regions. The current neighbourhood of the Sun is relatively sparse, making Gliese 710's approach stand out more sharply against the background rate. There is also the matter of stars not yet identified as close encounter candidates. Gaia's catalogue, comprehensive as it is, covers only a fraction of the Milky Way's stellar population with the precision needed for long-range trajectory prediction. Stars beyond a few thousand light-years, stars obscured by interstellar dust, and ultra-cool objects like brown dwarfs that fall below Gaia's detection threshold are absent from the encounter catalogues. The actual rate of close encounters past, present, and future is likely higher than current data suggest. Gliese 710 is the most prominent name on a list that is probably longer than we know, compiled using the best instruments ever built to study stellar motion, and still almost certainly incomplete. We are moving to. The framing of Gliese 710 as a star coming toward us is accurate, but it is only half the story. Every relative motion in astronomy involves two moving objects, and the solar system is not standing still, waiting for a visitor. It is hurtling through the Milky Way at approximately 828,000 kilometers per hour, a speed so large that stating it plainly barely helps, because human intuition has no natural scale for it. At that velocity, the solar system travels roughly 1 astronomical unit, the full Earth-Sun distance, every 6.5 days. In the time it takes to watch a film, the Sun and everything gravitationally attached to it has moved several million kilometers through the galaxy. This motion is not random. The solar system is in a roughly circular orbit around the center of the Milky Way, a supermassive black hole called Sagittarius A star, located approximately 26,000 light-years away. The orbital period of this journey is approximately 225 million years, a time span sometimes referred to as a cosmic year. The solar system has completed this orbit roughly 20 times since its formation. Over those 20 circuits, it has passed through regions of varying stellar density, traversed the edges of spiral arms, and experienced the galactic tide, the slow, diffuse gravitational influence of the Milky Way's overall mass distribution, which acts continuously on the Oort cloud and contributes to the steady background rate of cometary deliveries to the inner solar system. The direction of the solar system's galactic motion has an immediate consequence for the Gliese 710 encounter. The star is not approaching from directly ahead or directly behind in the solar system's galactic trajectory. It is coming from a direction approximately perpendicular to the galactic plane and slightly offset from the Sun's direction of travel, meaning the encounter geometry involves a combination of the solar system flying toward a point in space that Gliese 710 is simultaneously approaching from the other side. The relative velocity between the two objects, approximately 14 kilometers per second, is the net result of both motions combined. Without the solar system's own galactic velocity, the encounter would look different in both timing and geometry. This is not a unique circumstance. Every stellar encounter in the solar system's history has been a product of two moving objects converging through a shared medium, the galaxy, each on its own orbital path, each carrying the gravitational history of the objects bound to it. The galaxy is not a backdrop against which things happen, it is an active environment whose structure and mass distribution shape the trajectories of everything within it. It also means that predicting stellar encounters far into the future carries an additional layer of uncertainty beyond the measurement precision of individual stellar velocities. The solar system's own galactic orbit is subject to perturbations. Giant molecular clouds exert gravitational pulls as the Sun passes through or near them. The distribution of dark matter in the galactic disk influences the orbital dynamics of stars at scales far larger than any individual encounter. Over millions of years, small uncertainties in the solar system's current velocity compound into meaningful uncertainties in its future position. The most reliable encounter predictions, including Gliese 710, are those within the next 2 to 3 million years, where current velocity measurements remain sufficiently accurate that the accumulated uncertainty has not yet grown large enough to change the fundamental character of the encounter. Beyond that window, the trajectories blur, and the precise geography of which stars will come close and when becomes increasingly probabilistic. Two objects moving through the same galaxy, each unaware of the other, each carrying their own worlds, converging on a point in space-time that neither chose. Gaia's discovery. In the spring of 2013, a spacecraft the shape of a spinning top was launched from the Guiana Space Center in Kourou, French Guiana, and positioned at the second Lagrange point of the Earth-Sun system, a gravitationally stable location, roughly 1.5 million kilometers from Earth in the direction away from the Sunday. Its name was Gaia, and its purpose was singular in the history of astronomy: to measure the positions, distances, and motions of stars across the Milky Way with a precision that no previous instrument had approached. What Gaia ultimately revealed about Gliese 710 rewrote the risk assessment for our solar system's future. Gaia's operating principle is astrometry, the precise measurement of stellar positions. The spacecraft rotates slowly on its axis, scanning the sky continuously, each rotation sweeping 2 telescopes across different regions of the celestial sphere simultaneously. Over the course of its mission, Gaia observed each star it could detect dozens of times, building up a dataset of positional measurements whose combined statistical power reduced individual position uncertainties to levels measured in micro-arc seconds. 1 micro-arc second is equivalent to the angular size of a €2 coin placed on the surface of the Moon as seen from Earth. That is the level of precision Gaia achieved for the brightest stars in its catalogue. From positional measurements alone, Gaia extracted stellar distances through parallax, the apparent shift in a star's position as Earth moves around the Sun over the course of a year. The larger the shift, the closer the star. Combined with measurements of how stars move across the sky over time, and supplemented by radial velocity data from an onboard spectrometer for the brightest stars, Gaia constructed a complete 3-dimensional velocity map for over 1 billion stellar objects. The first major data release came in 2016. The second, in April 2018, was transformative. For Gliese 710 specifically, the Hipparcos satellite, Gaia's predecessor, had measured the star's parallax and proper motion in the 1990s with an uncertainty of roughly 1 milliarc second. Those measurements had placed the star's closest approach distance at approximately 1.1 light-years, a figure that was notable but not alarming. Gaia's second data release reduced the uncertainty on Gliese 710's proper motion by a factor of roughly 40. The revised measurements showed that the star's trajectory was aimed more directly at the solar system than Hipparcos had been able to determine. The revised closest approach distance dropped to approximately 0.065 light-years, 4,000 astronomical units, with an uncertainty small enough to place the encounter firmly inside the Oort cloud across virtually all scenarios within the error bounds. The paper that first reported this revised figure, published by Baylor Jones and colleagues in astronomy and astrophysics in 2018, noted that Gliese 710's encounter stood out from all other stars in the Gaia catalogue, not just in terms of closest approach distance, but in terms of encounter duration, the length of time the star would spend within the DE, the solar system's gravitational neighbourhood at close range, a consequence of its low relative velocity. No other star in the catalogue combined proximity and slowness in quite the same way. Gaia has since continued operating, with its third major data release in 2022, extending the catalogue and refining existing measurements further. The Gliese 710 parameters have remained stable across these successive releases, a sign that the original Gaia measurement was sound, and that the encounter, as characterized, is not an artifact of measurement error but a confirmed feature of the local stellar environment. The technology existed for decades before it was precise enough to find what the sky was hiding, what it looks like. The night sky 1,360,000 years from now will be unrecognizable to eyes that know the current constellations. Every star visible tonight has been drifting slowly across the sky for millions of years, and over that span of time, the familiar patterns Orion, Cassiopeia, the Southern Cross will have dissolved entirely, their member stars scattered across different regions of the sky by their individual galactic motions. The sky of the far future is a different sky, and in that sky, Gliese 710 will burn as something no star has appeared to human observers for all of recorded history, a genuine rival to the night. At its closest approach of roughly 4,000 astronomical units, Gliese 710 will be approximately 330 times closer to Earth than it is today. Apparent brightness in astronomy scales with the inverse square of distance, meaning that halving the distance makes an object 4 times brighter. Compressing the distance by a factor of 330 produces a brightness increase of more than 100,000 times. Today, Gliese 710 sits at an apparent magnitude of approximately 9.7, faint enough that it requires binoculars or a small telescope to see at all. At closest approach, Applying the inverse square law to the geometry of the encounter, it will reach an apparent magnitude of roughly 0.5, placing it among the brightest stars in the sky and comparable in brightness to Canopus, currently the second brightest star as seen from Earth. Magnitude 0.5 means Gliese 710 will be clearly visible in daylight under the right conditions, and at night it will cast faint shadows. Its colour, the warm amber orange of a K-type main sequence star, with a surface temperature around 4,300 degrees Celsius, will tint the light it casts. It will not be the white-blue of Sirius or Vega. It will glow like a distant ember, steady and orange against the dark, bright enough to read by on a cloudless night if you held the page at the right angle. The approach will not be sudden. Over hundreds of thousands of years preceding closest approach, Gliese 710 will gradually brighten, crossing the threshold of naked eye visibility roughly 200 to 300,000 years before its closest point, and continuing to intensify as the distance closes. For whatever form of observation exists in that era, the star's brightening will be a measurable, trackable phenomenon long before it becomes dramatically visible. Its motion against the background sky will accelerate as it approaches. Proper motion that is currently less than 1 milliarcsecond per year will increase sharply over the final tens of thousands of years, giving Gliese 710 a perceptible drift across the sky on timescales of centuries rather than millennia. Following closest approach, the process reverses. Gliese 710 will begin to recede, dimming over hundreds of thousands of years, fading back below naked eye visibility, and eventually retreating to its current obscurity as another point of dim light in a catalogue of stellar neighbours. Its passage through the sky will leave no permanent visible mark on the night. The constellations will continue their own slow dissolution, driven by proper motion, indifferent to the visitor that passed through. The sky keeps its own record of these encounters in other ways. In the orbital histories of comets, in the statistical distribution of Oort cloud populations, in the long geological memory of cratered surfaces, the visual spectacle fades. The gravitational memory does not.